Fresnel's BIPRISM to determine wavelength of given source. So here the main purpose of Fresnel's BIPRISM is to produce coherent sources, right? Now this is the BIPRISM. Now S1 and S2 are two coherent sources. The distance between these two is 2D, and the distance between these coherent sources to the screen is capital D. Okay. Now this is the overlapping region, okay, where we find sustained interference pattern. Now here our intention is to determine the wavelength of a given light or given source. Now here, to determine the wavelength, we have to make certain adjustments. So now, to determine this wavelength, we require an optical bench. So this optical bench consists of 3 stands. First stand, second stand and third stand. Okay. In first stand, we will place the slit. In second stand, we will place the required Fresnel's BIPRISM. In third stand, we will place a eyepiece. Okay. Now, using spirit level. So spirit level means in particular wooden frame there will be a spirit. Solely we call it as a spirit bubble. We call it as spirit level. Now to adjust these 3 stands in a same level, we will use spirit level. If a bubble is at the center, then it shows that these are in same level. If not, we have to adjust them. So the first step, by using spirit level, we will adjust these 3 stands parallel to this optical bench, and we will arrange these 3 stands at the same height. The height must be same. We arrange these 3 stands at the same height. Okay. Now we know that in eyepiece we will have cross wires in such a way. We call them as cross wires. In eyepiece we will have cross wires. Okay. And now first we will adjust eyepiece such that we can see cross wires clearly. We have to adjust eyepiece in such a way that we have to see cross wires clearly. Now first here we arranged that particular source whose wavelength has to be determined. Here we are using a monochromatic light, that is sodium light. First what we will do means, first we will narrow this slit. Okay, we will narrow this slit. After that we will allow this sodium light to incident on this slit. Now why we are narrowing the slit means to produce parallel beam of light. We are narrowing the slit. Now from this slit the light comes and falls on our BIPRISM. Now BIPRISM is connected with a handle. Through this, we can rotate the biprism, and also this biprism can be moved to the right angles to this optical bench. With the help of a handle, we can rotate the biprism, and at the same time, this stand in which biprism is placed can be moved at right angles to this optical bench, right? Just now, by moving this biprism, we will move this biprism until overlapping region is viewed through eyepiece. So, we will move this biprism to the right angles of optical bench. Up to when we are moving? Until the overlapping region is viewed. Okay. Now next, by using the tangent screw of a slit, we will rotate the tangent screw of the slit until fringes appear, interference fringes appear clearly. Okay, until interference fringes appear clearly. So first what we are doing, we are narrowing the slit, sodium light comes and fall on it. From there, this light fall on the biprism. By moving the biprism to the right angles to the optical bench, we will move this biprism to the right angles to the optical bench until the overlapping region is founded. After overlapping region is viewed, we will rotate the screw arranged to the slit until a clear fringes appear. Now how will be the interference pattern? Means the interference pattern will be in such a way. These are dark bands, bright band, dark band, bright band. So interference pattern consists of alternate dark and bright bands. These only we call it as fringes. Dark fringes, bright fringes. These are equally spaced with each other. Okay. And now until this region is viewed clearly, we just move the biprism to the right angles to the optical bench. Right. Now, if we move this eyepiece, we find that away from the biprism, if we move eyepiece away from the biprism, we see that fringes move to sideways. Fringes move to sideways means lateral shift has taken place. Okay. So, here the reason for this lateral shifting of fringes is that the line joining slit and biprism are not parallel to the length of optical bench. The reason for this lateral shift is the line joining the slit and biprism are not parallel to the optical bench. So we have to remove this lateral shift. Then only we can find a sustained interference pattern. So now we got a sustained interference pattern. Now let us see the procedure how to determine the wavelength of this sodium light. Now here the procedure involves the 3 steps. So before going for that steps, let us see the formula related to the wavelength of given light. It is lambda equal to beta into 2d by d. Beta we call it as fringe width. This is nothing but space between successive maxima, that is bright fringes, or minimas, that is any 2 successive dark fringes. Next 2d, it is the distance between 2 virtual sources, and capital D, distance between slit and eyepiece. Okay. So now here first we have to find beta, fringe width. So to finding beta, what we will do means, we are having the crosswires in the eyepiece, no? First we will set the crosswire on one bright fringe, first bright fringe. We will note the micrometer screw reading, and again we will move and adjust the crosswire on the next successive bright fringe, and again note the micrometer reading, and the mean value of these two readings gives the value for beta. So in such a way we will calculate beta. So we will adjust the crosswire, the vertical crosswire on the one of the bright fringe. We will note the reading, and again we will adjust the vertical crosswire on other bright fringe, and we will note the reading. Right? Now next we have to calculate capital D. So by using the scale itself only, we will calculate the distance between the virtual sources and the screen. Okay, we will calculate the distance between slit and eyepiece by using the scale itself only. Now the third part is, we have to find 2D. That is, directly we cannot find the distance between two coherent sources because these are virtual sources. By using the scale we cannot find because these are the virtual sources. So now here, to find that, what we will do means, we will take a convex lens of a very short focal length. We will take a convex lens of very short focal length. Now here we will have a slit. I didn't denote it in the diagram. Here we will have a slit, then biprism. Now between biprism and eyepiece we will place this convex lens. We will not disturb the position of a slit, okay, biprism. Just we will move the eyepiece, okay, we will just move the eyepiece and adjust the distance of this convex lens such that the distance is 4 times the distance. We will adjust the distance in such a way that the distance is 4 times the distance of focal length. Okay, the distance is 4 times the distance of focal length. Here we are not disturbing slit or biprism. We are just disturbing the eyepiece, and we are adjusting the convex lens distance in such a way that the distance of this convex lens is 4 times that of its focal length. Right? Now after adjusting the position of convex lens, first we will move the convex lens towards the slit. We are moving this convex lens towards the slit. At one particular position you say L1. At one particular position you say L1, we find these two images A1 and B1. Two images A1 and B1. At that position we will fix the convex lens. By using micrometer screw we will note the distance D1, and U is the object distance, that is distance between slit and convex lens, and V is the image distance. Now after that, now again we will start moving convex lens towards eyepiece. Now towards eyepiece. Now say at one particular position L2, we will find some diminished images A to B2. Now after observing these diminished images with the help of micrometer screw, we will find the distance D2, and this is the object distance U up to convex lens and eyepiece, and this is the image distance V. Now after noting these D1 and D2 by using conjugate foci principle, so we will write D1 by 2D equal to V by U, D2 by 2D equal to U by V. We will multiply to D1 into D2 by 2d whole square equal to v by u into u by v. d1 d2 by 2d whole square equal to 1, or 2d square is equal to d1 d2, or 2d equal to under root d1 d2. In such a way, we got the value of 2d. By substituting d beta 2d in the required formula, beta 2d by d, we will get the wavelength of the required source or light we used. So in such a way, we will determine the wavelength using Fresnel's biprism.